Hi everyone, Mr. Boltri here bringing you video 7.3, where we're going to talk about Kepler's three laws of orbit. So it's going to be pretty simple. We're going to talk about Kepler's first law, Kepler's second law, and then finish with his third law. So his first law says, pretty simply, that the orbit of a planet is an ellipse with the sun at one of the foci. So you guys have studied ellipses before, so I don't need to talk about this too much, but here's what an ellipse looks like. It has two foci. The sun is going to be one of them, and then the planet is going to orbit around the sun in an elliptical fashion. So just some vocabulary that I was going to say that you need to know, but you don't really need to know all that much, but it's just important. It's useful to know in case it does ever come up, is that we have something called the major axis, which is 2 times A, which I've marked here. So A is the semi-major axis. B is the semi-minor axis, because 2B is the minor axis, and something called the eccentricity is C divided by A. And that basically is a measure of how elliptical, how spread out the elliptical orbit is. And that's an important number because I'm going to ask you, what would the orbit look like for something that had an eccentricity of 0? Well, that would mean that the C is basically non-existent, which would mean that it would look like a circle. And this is important to know because we can actually measure the eccentricity of the rotation of different planets and stuff. And we can find that many planets have a rotation, an eccentricity that is very close to 0. For example, Earth's is 0.017. And this is important because it allows us to treat the orbits of most of the planets, including Earth, as basically circles, which simplifies all of our calculations and stuff. And it's just important to be able to say that with a little bit of confidence that it is, this is an oversimplification, but it's not a gross oversimplification that makes our calculations totally pointless and useless. So the ellipse of the Earth's orbit and most orbits are basically circles, even though they're not exactly circles. And circle is a type of ellipse, so it doesn't break Kepler's first law. Kepler's second law has to do with the areas swept out by the orbit of the planet. So I'll read this to you. A line segment joining a planet and the sun sweeps out equal areas during equal intervals of time. So if we treat these, let's say this is 2 hours over here and 2 hours over here. So if it goes from point A to B in 2 hours, and then we sweep out some area from the sun to the planet. Then over here, let's say from point C to D, it's going to sweep out a different amount of area or a new area. And actually, what Kepler's second law says is that A1 equals A2. So why is this important? Why are we learning this? Why is this a law in the first place? And we're learning it, and it's important because it is it relies on and is an application of the principles of conservation of energy, which we've already learned, and conservation of angular momentum, which we're going to learn next semester. So it's a really good application of both of these. So the reason why these areas are the same is because over here, the object is very close to the sun, so it has very low gravitational potential energy, and therefore it has very high kinetic energy. So in that same delta t, then that same time interval, that let's say 2 hours or whatever, it's going to sweep out a lot larger, it's going to go a farther distance, but because it's close to the sun, the area is not going to be super large, as opposed to over here has a lot of gravitational potential energy, so a very small amount of kinetic energy, so it's not going to go very far, but because it's so far from the sun, the area is still going to be rather large. So that's how A1 is able to equal A2. These two areas are able to be equal. And then we'll revisit the same concept next semester when we've learned about conservation of angular momentum, which will allow us to actually solve for even more quantities in this setup. But just using the conservation of energy, which we already know, we should be able to understand why this is true and also solve for the kinetic energy and the gravitational potential energy at different points in the motion of the planet, which is why these two areas are equal. And last but not least, Kepler's third law says that the square of a planet's orbital period is proportional to the length of the semi-major axis of the orbit cubed. It should say cubed in here, is proportional to the cube of the length of the semi-major axis. What does this mean? Again, why is this important? Why are we studying this? Why is this here? And I'll show you very quickly because, again, this is an application of some of the stuff that we've already talked about. Specifically, if we set the gravitational force to equal the centripetal force, which is causing the object to stay in its orbit, then we know the formula for the universal force of gravity is big G times the mass of the sun times the mass of the planet over the distance between their centers of mass squared. We've already talked about this. And then the centripetal force is going to be the mass times the centripetal acceleration. And we've talked about in the past that centripetal acceleration equals v squared over r, which is this is the radius of the circle or whatever that we're traveling in. So then we can simplify this because we notice the mass of the planet is on both sides, so we can cross that out. And so then we get a simpler form of the equation that doesn't have the mass of the planet. Now, and here's another important thing is remember this little r in the bottom of our force gravity equation does not equal the radius always, but in this circumstance, the radius of the orbit is going to equal the distance between the two centers of mass. So we can say that those two r's are equal, which allows us to simplify our equation even further. So we get this actually pretty simple equation. Which we're going to clean up just a little bit because we know that the object is moving in a circle. So for a circle, the velocity is going to be the change in distance or the displacement over the change in time, which for a one circle is going to be 2 pi r divided by the time it takes to get around one circle, and we call that the period. So we call it the period. 2 pi r divided by the period equals the velocity. We can substitute that in for the velocity. Get 2 pi r over the period squared equals this simplified version of the force. And we can then square everything and solve for the period. So we get the period squared is proportional to the radius of the circle cubed times 4 pi squared divided by the universal gravitational constant times the mass of the object that's rotating around, which was a long way of saying that this is Kepler's way of proving, and this is kind of a derivation because you guys know that I like to do derivations, that the period squared is proportional to the radius cubed, which, and then that's all multiplied by, you'll notice that 4, pi, g, and the mass of the sun are all constants in this problem. So except for some constants, the only thing that we have to solve for is a period and radius. And this is a really good problem that they like to do linearizations on, because if you were given period and the radius, if you wanted to graph something that would be linear, you would have to graph period squared on one axis and radius cubed on the other axis. Then when you solve for the slope, it would be this function. And you could actually solve for this. Let's say if I were to write this question, I would say, okay, graph this, find the slope, and then solve the slope for the mass of the sun by dividing out the different constants that we have in the problem. So that's one thing that they might ask you to do with this. So just to circle back around and revisit, we said that Kepler's third law was the period squared is equal to the semi-major axis cubed. So how do we get from A to R? And that's this R, which is treating it like a circle. And the A is, this actually works for all ellipses, not just circles. But as far as the AP exam is concerned, you only have to know how to sort of derive this formula from for a circle. And the biggest thing to derive from there, the two things that you need to know to derive this is to start from the gravitational force equals the centripetal force, substitute things out, and then you know the velocity is 2 pi r over the period, and that's for a circle. So this formula is not on your formula sheet, nor do you need to memorize it. You do not need to memorize it. That would be taking up too much of your brain space in order to memorize it. You just need to be able to quickly derive it if you need to use this formula on a, probably it won't come up in a multiple choice question. You won't have to like substitute in values. I think it's more likely to come up in an FRQ, and you'll have the time to just take 1 minute, 1 or 2 minutes to go through this quick derivation process again. The trickiest thing, like I said, is substituting in for V right here. So the last important thing about Kepler's third law is that the period of the orbit is independent of the mass of the orbiting object. So this is just so important because yes, it does. The period does depend on the radius. but it does not depend on the mass of the object. So this is important for satellites that are orbiting around Earth. When we have questions about the period of the satellites orbiting around Earth, and we change the mass of the satellite, is as long as it's orbiting at the same radius. If the radius is different, then the period is going to be different. But if the radius is the same, then the period is going to be the same regardless of mass. And that's because from where we had before, where we had the mass of the planet on the left side and the mass of the planet on the right side. And when I say planet, I mean the object that is orbiting. So this is the last and most important thing to remember about Kepler's third law. So that was a lot of new information about Kepler's three laws. And in our next class, we're going to do some practice problems, applying them and looking at the orbits of different objects. You're going to get more practice like sketching the orbits of objects and recognizing what objects are orbiting when and how in our next class. So please let me know if you do have any questions. But until then, go Bears.